Hello everyone, I am Muhammad Yahya. Welcome to the course Electronic Devices and Circuits. This lecture targets third semester Diploma Electronics Engineering students. The prerequisite for this is a basic know-how on transistor which everyone studied in second semester. But considering the COVID-19 pandemic situation, I would like to attempt a quick recap of fourth module of basic electronics so that those who lost those classes can make use of it. Transistor was invented in 1948 by John Bardeen, Walter Brattain, and William Shockley at Bell Laboratories in United States of America. Structure of a transistor. The transistor containing three separate regions. It can either be NPN or PNP type. Middle region is called the base. The outer regions are called emitter and collector. Collector region is made larger than emitter. Base is lightly doped and very thin. Emitter is heavily doped. Doping of collector is between that of emitter and base. Structure of a transistor. The transistor containing three separate regions. It can either be NPN or PNP type. Middle region is called the base. The outer regions are called emitter and collector. Transistor has two PN junctions, emitter base junction and collector base junction. Emitter base junction can be denoted by a diode and collector base junction by another diode. It is shown in the figure below. There are four possible ways of biasing these two junctions. Emitter junction is forward biased and collector base junction is reverse biased. That region of operation is known as active region of operation. If both emitter junction and collector junctions are forward biased, that condition is known as saturation. If both emitter junction and collector junction are reverse biased, that condition is known as cutoff. If someone biasing emitter junction reverse and collector junction forward, that condition is known as inverted mode of operation. Mode of operation is used for continuously variable signal. Saturation and cutoff are used in switching transistor or in digital signals. Input circuit, emitter base junction has low resistance because of forward bias, whereas output circuit, collector base junction has high resistance due to reverse bias. Input emitter current almost entirely flows in the collector circuit. Therefore, a transistor transfers the input signal current from a low resistance circuit to a high resistance circuit. Contracting the two terms, transfer and resistor, results in the name transistor. That is, transfer plus resistor gives transistor. We have seen that transistor can be connected in any one of the three configurations. It behaves differently in different configurations. In which configuration should we connect a transistor? This depends upon the particular application we desire. The parameters that govern the suitability of the configuration are dynamic input resistance, dynamic output resistance, DC current gain, AC voltage gain, and leakage current of the transistor in a given configuration. Out of the three configurations, common collector configuration has maximum input dynamic resistance about 750 kilo ohm. So we use this configuration where high input resistance is involved. Even though its voltage gain is less than unity, the decreased voltage gain can be compensated by subsequently using the CE configuration. The input resistance of a common base configuration is very low as 100 ohm. Input resistance of a common emitter may be about 750 ohm or below 1 kilo ohm. Output resistance is very high for a common base resistance. It is about 450 kilo ohm to 1 mega ohm. The output resistance of a common emitter transistor is high, about 10 kilo ohm to 50 kilo ohm. Voltage gain is high for common base and common emitter and less than 1 for common collector configuration. Current gain is less than 1 for common base amplifier and very high for common emitter amplifier. Common collector amplifier is used for impedance matching. Common emitter configuration. IB and VB are the input variables. The output variables are IC and VCE. We can use the circuit arrangement shown in figure to determine the input characteristics of an NPN transistor. Input characteristics are shown in figure. They relate IB to VBE for different values of VCE. For a given value of VCE, the curve is just like the diode characteristics of a forward bias region. Here, the emitter base is PN junction diode, which is forward biased. This junction becomes a better diode as VCE increases. That is, there will be a greater IE for a given VBE as the VCE increases, although the effect is very small. From the above circuit arrangement, we can also determine the output characteristics of an NPN transistor. Figure shows typical output characteristics of an NPN transistor. They relate the output current IC to the voltage between the collector and emitter VCE for various values of input current IB. Note that the quantities VCE, IC and IB are all positive for an NPN transistor. If the transistor is PNP type, we reverse the terminals of the batteries VCC and VBB so that VCE, IC and IB become negative. In the active region, IC increases slowly as VCE increases. When VCE is below a few tenths of a volt, IC increases rapidly as VCE increases. In this condition, both junctions of the transistor are forward biased. The transistor is working in the saturation region. It is called saturation region because the collector current IC no longer depends upon the input current IB. In the active region, a small input current IB produces a large output current IC. The collector current is not zero when IB is zero. It has a value of ICEO, the reverse leakage current. The current ICEO is related with ICBO. Below IB is equal to 0, both junctions are reverse biased. That region is known as cutoff region. Current relations. In a transistor, IE is equal to IC plus IB. If we let IC and IB change by small amounts delta IC and delta IB so that IE changes by delta IE, we have delta IE is equal to delta IC plus delta IB. Then delta IB is equal to delta IE minus delta IC. The current amplification factor beta in a common emitter amplifier is equal to delta IC divided by delta IB. It can be rewritten as beta is equal to delta IC divided by delta IE minus delta IC because delta IB is equal to delta IE minus delta IC. If we are dividing numerator and denominator by delta IE, we will get beta is equal to delta IC divided by delta IE divided by delta IE divided by delta IE minus delta IC divided by delta IE. Delta IC divided by delta IE is equal to alpha. Then the relation becomes alpha divided by 1 minus alpha. Beta is equal to alpha divided by 1 minus alpha. Now we had concluded the last module of basic electronics. Please send the questions. Transistor as amplifier will be continued in the next video. Let me stop here.